began according to plan as they leapt off the bridge while tethered to the cable.
Stand up.
80 feet,
All right, guys, you've seen this a number of times, so I'm just going to focus on a few things.
80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside helmet cam. Kenny, myself, boy, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reaches about 78 miles an hour, right about here, 78 miles an hour.
Notice that he's not saying 80 miles per hour. He's saying 78 miles per hour. All right. How do you know that they're going to be moving at 78 miles per hour? Well, as soon as he said that, I got suspicious because the announcer said 80 miles per hour. This guy says 78 miles per hour. I knew the length of the cable. That's like 200 feet. Knowing the length of the cable, I knew that we're going to go at 78 miles per hour. How? That's something that you will find out next week. All right. There's a bit of a puzzle here. Only thing I knew at that point was this was calculated. All right. These guys are daredevils. They knew what they were doing. All right. This was a calculated risk. This was intentional. So which told me that they also calculated the amount of tension that they were going to induce on the cable. So the cable that these people bought must have been the right cable. So the question is, what's next? All right.
We'll see the
So the question is, how did they know how much tension that they were going to induce on the cable? And on top of that, obviously they overlooked something. So the question is, why?
disconnect.
Right, so that's one of the questions.
The speed is critical. I need to make sure that I hit the magic number to drive through the loop. Otherwise, it's not going to be possible. So I had to concentrate on that and just calm myself down. I was probably the most calmest that I've been all day.
So this is done on the 80th year anniversary of Jaguar.
When I was in there and I was driving down.
Of course, the speed is critical, right? Because you have to loop the loop. If you don't reach the speed, well, you're not going to be looping the loop. That's for sure.
Approaching the loop.
So how do they know what the speed is? You can't do trial and error, so it needs to be calculated. So you can exceed the speed, but you cannot be under that speed. That looks impressive, right? Jaguar took him 80 years to be able to do the loop-to-loop. Out of our Tempo,
You're looking at style and technology in total harmony.
was able to do it in 1980.
It's the new 84 Ford Tempo. Tempo's unique aerodynamic design contributes some mileage this high. There's technology like four-wheel independent suspension to absorb impact. A new high-swirl combustion engine gives Tempo quick power response. And Tempo's front-wheel drive delivers responsive handling and good traction. The new Ford Tempo.
I have no idea why they decided to loop-to-loop on a commercial.
Have you driven the best built
This is from 1980.
American cars? Have you driven a Ford lately?
So how do you know what the magic number is?
All
How
right,
do you
the first
calculate
ride is going to be
it? Oh,
a
I got it.
gradual onset ride to a maximum of 7 Gs. Are you ready?
Yeah, right. Sure.
Are you ready?
Yes, sir. I'm ready.
Ready. 3, 2, 1, engage. How you doing?
If you lose all the green, tell me now and start that lower body straight, okay?
Okay.
Squeeze those legs nice and tight. 1, 2, breathe. You're looking real good. Squeeze everything nice and tight.
I'm losing it.
Not yet. It's only 2 Gs.
Okay.
It's only 2 Gs.
You should feel like you're going straight up in the air at this point.
This is awesome.
The 4G right there, you're doing good.
3, 2, 1, engage. Back on the stick. On top. On top, breathe. You're on top, breathe. You're on top, breathe.
I'm losing the green.
Okay, big breath, walk out and hold it.
You're on top, breathe. Hold. On top, breathe. 1, 2, breathe.
1, 2, 3. No cheater breath.
1, 2, breathe. 1, 2, breathe. 1, 2, breathe.
All right?
Legs tight. Foot tight. Breathe.
1, 2, 3.
1, 2. Hold. Okay.
Where am I on this?
Stay tight. Stay tight. Stay tight. Stay tight. Hello. Are you with me? You coming back around? Hello. How you doing?
What?
Hello, Will.
Hello.
Will, sit up.
I'm up.
Sit up.
What?
You're up. Put your head up.
It is up.
Put your head up.
Oh.
Do you know what happened?
Yeah.
You ate lock.
Yeah.
Happened.
I'm taking ID lock.
All right.
Okay, all right? You feel nauseated?
Yeah, a little bit. I'm gonna vomit.
Okay, get the bag. Get the bag.
It was a big jerk.
And to be honest, she's the only one.
I actually have no comments for you. Everything was real
Did relief. Did fine.
good.
She's the only one that didn't pass out.
How you feel?
So the question is, how did they know how fast to spin this thing, right? So they know that when induced about 5, 6, or 7 Gs. So how do they know how fast to spin it? So that becomes the question. All right. So force acting on the mass is going to cause it to accelerate. So this is your acceleration term. All right. It's Newton's second law, right? acceleration term that you're looking at is the centripetal acceleration. So this is in circular motion. This is the acceleration which is directed towards the center. In essence, it kind of gets interesting because inside a centrifuge, or it's known as a
The centerpost, the cameraman films dizzy doings as the more daring of the rotor riders defy centrifugal
So they spin it so fast that it becomes suspended on a wall.
force.
If you've ever done this, give yourself 5 points. That's a fun little experience. All right. If you close your eyes, it's going to feel like you're laying down on your bed.
Or try. The rotor ride is a snap unless you're the squeamish sort.
And then they lower the floor, and every single person becomes suspended. So when you're inside a rotor like this, what is this centripetal force? When somebody asks you that question, what does it mean to you? All right. It doesn't mean much to anyone at this point because you guys kind of make the connection immediately. Centripetal force, translated to English, means any force directed towards the center, any force directed towards the center of a circle. It's a center-directed force, center-seeking force. All right, so what is the force? Centripetal force. What is the force which is directed towards the center when you're inside a centrifuge, just like that? That's the question. All right, now you have to look at it this way. What prevents you from going in a straight line at a constant speed when you're inside the centrifuge? Answer to that question is simple, right? Wall does. You want to go in a straight line at constant speed, but you can't because there's a wall there. So the wall is going to apply a force on you, right? So it's going to be a surface force, the normal force. The normal force, or the surface force, is what's directed towards the center. So that becomes the centripetal force. You got a satellite orbiting the Earth. So what's the centripetal force in this case? Once again, centripetal force means any force directed towards the center, directed towards or away from the center of the circle. In this case, force which is directed towards the center is the gravitational force. So what's the centripetal force whenever you're negotiating a curve like this? What prevents you from going in a straight line at constant speed? What prevents you from going in a straight line at constant speed is the frictional force. It's the static frictional force. When you maximize the static friction, it's going to go kinetic. It turns into sliding. So the static frictional force is what keeps you on the road. Static frictional force is the force which is directed towards the center. Static frictional force is the force which is the centripetal force in this case. All right, so those are the 3 examples that we look at. Right, so our topic is we're going to be dealing with the centripetal force this time. All right, circular motion implies that there's an acceleration directed towards the center. All right, so this is your centripetal acceleration, something that we discussed before. So the acceleration is going to be caused by a force in the same direction. So that's known as the centripetal force. All right, so substitute the acceleration formula and it turns into a centripetal force formula. That's it. Now, centripetal force is any force directed towards the center of a circle, right? All right, so here's your centrifuge. The person becomes suspended on the wall. The reason why the person is not able to move in a straight line at constant speed because of the wall, the surface force from the wall, right? So centripetal force in this case is going to be the normal force. All right, so that's going to be your normal force. All right. Satellite orbiting the Earth, the centripetal force is going to be gravity. Car rounding a curve, the centripetal force is going to be static frictional force. Review.
It is such a tremendous amount of energy. Yet the limits within which it must fly are very, very narrow. So you've got something that's powerful, but delicate at the same time.
The propellants that they use on the space shuttle are very, very potent, and it's like a gigantic controlled explosion that lasts for 8 minutes to get you in orbit. The space shuttle main engines are a very incredible device. They generate enough force to levitate 200 cars, and they could hover them stationary midair. The fuel amount used is tremendous. The turbo pumps that supply fuel to the engines pump enough liquid it could drain a swimming pool in less than 30 seconds.
Space begins at the edge of the Earth's atmosphere, 50 miles straight up. But the shuttle orbits at an altitude of about 180 miles.
We've become accustomed to seeing the shuttle up there, seemingly suspended, hardly moving. Yet the astronauts are traveling around the Earth at 18,000 miles an hour. And as they go about their work, they can glance up at 16 sunrises in a single day.
Now, here's a statement at the end.
Hardly moving. Earth at 18,000 miles.
18,000 miles per hour. You say 18,000 miles per hour. 18,000 miles per hour. I say 17,500 miles per hour. How do I know? All right, guys, you can look this up, obviously. The way we do it is we calculate this sort of stuff. All right. So what's the required speed for a space shuttle to remain in orbit if it's located 180 miles from the surface of the Earth? Okay, so we'll do some just standard problems. While you guys are studying for the task, just go over each and every single problem and make sure that you guys know how to set them up. All right, these are really straightforward problems. All right, the first thing you need to do is just draw this out so you can see the details. All right, so the speed is what we're interested in. It's going to be located 180 miles from the surface of the Earth. So I'm going to use D for that distance. Radius of the Earth is this. So it's something that I memorized it by looking up. It's the average radius. So the question is how fast? How fast does it need to move? How fast does it need to move in order to remain in orbit around the Earth? All right, and then we have the radial distance from the center of the Earth to the space shuttle. So it's going to be this distance, which is 180 miles plus the radius of the Earth. All right, next thing we need to do is we got to do the conversions. the metric units, obviously. This needs to be expressed in terms of meters, and that's it. And then we need to get the numbers. All right, centripetal force is caused by gravity. All right, so here's a generic formula for the centripetal force. Here's a formula for gravity, gravitational force. All right, so they're going to be equal to each other, so do a back substitution. And then the only thing you have to do is literally solve for V. All right, so how do you solve for V? Get rid of M, and then multiply both sides by R. All right, so we are get rid of M. So mass of the space shuttle is going to, all right, so the mass of the space shuttle is going to cancel. You get an R here, you get an R squared here. All right, so which means that you can cancel one of the R's from here with that one. Or it's the same as multiplying both sides by R. Here's the final equation. So what do we have? We got the strength of gravity. We got the mass of the Earth, and we got R. So R is going to be stuff at this point. Okay, so we know the mass of the Earth, we know G, and we know R. Okay, so now let's get the numbers. R is going to be the radius plus the distance to the space shuttle. So that's the final equation. All right, so the numbers are the ones that we need to get. All right, so notice that things were not converted to the metric unit. So let's get what we need. So mass of the Earth, you kind of look it up. We know what G is. Here's the mass of the Earth. R plus D is going to be this number plus that number. So we need to convert this to meters. This is already in meters, so both of them are converted. And then let's get the expression for the radius at that point. And okay, so we'll get an expression for the radius. Get back. All right, so here's the radius, and then plug the numbers in. This is not going to be 17,500. The actual number is going to be 17,000 and almost 300. So I'm going to approximate that to be 17,500. All right, it's a better approximation than 18,000 miles per hour. All right, let me just get back to the important portion of the solution. The important portion of the solution is how you set this up, guys. You're looking for V. This is circular motion, and you know that the centripetal force is going to be the same as the gravitational force. All right, the most difficult portion of these problems are usually the initial setup. How do you initially set this thing up? And that's it. All right, so initially you set this up and you're looking for speed. Speed is going to be coming from the generic centripetal force formula. All right, and then the rest is algebra. It just works out. All right, so these are the numbers, and this is the formula that you come up with, and then you plug the numbers in. It's going to give you roughly about 17,500 miles per hour. All right, this is a simple enough problem. Rotors. Okay, here's a question for the rotors. You know you want everyone to be suspended on the wall, right? Inside the rotor. So you have a 100-pound kid, so you spin it so fast. But what if someone who's about 400 pounds walks in, like a linebacker, all right? And you also want that person to be suspended on the wall. So does this mean that you have to actually spin it harder? All right. I mean, do they have like weight limits? Somebody just walks in, this guy's 400 pounds, and you want this person to enjoy the experience as well. So does this mean that you have to throttle it up, or can you keep it at the same speed? So the required speed for centrifuge, so that every single person is suspended on the wall, does that change depending upon the weight of the person? So that's what we will get in that video. So does the weight matter in terms of how fast you need to spin this? So every single person is suspended on the wall. All right, so let's figure out the minimum required speed in order to keep every single person suspended on the wall. So this is going to be from number 2. It's their rotor. All right, so the minimum required speed, V, is what you're looking at. So we need to express it in terms of miles per hour. All right, so what's the minimum required speed for every single person to become suspended on the wall? All right. What I'm going to do is, here's the center of mass. Okay, this is my radial axis. All right, this is the y-axis. Along the y-axis, there's going to be weight. All right, the reason why the person is going to become suspended because of frictional force is going to be in the opposite direction. So you want this friction to be the static frictional force. And then along the radial direction, this person is going to be pushed up against the wall. So there's going to be a reaction force from the wall. So that's the normal force. All right, so I did my force diagram. Coefficient of friction for the static friction in this case, it depends on the slipperiest outfit someone could wear. So let's assume that it's 0.33. And we got a 100-pound kid and a 400-pound adult. All right, so what's the minimum required speed? When we go from the kid to the adult, we get the same. We get the same speed. I need coffee. All right, how do you do this problem? Once again, you're interested in speed. All right, so centripetal force, same as the normal force. Here's your generic centripetal force formula. Here's your generic centripetal force formula. Okay, R is going to be 15 feet. I'll do the conversions later. All right, so do a back substitution. Now your speed is right here. Your speed is always going to come from this generic centripetal force formula. All right. Solve for V. So how do you do it? Get rid of M, multiply both sides by M, and get rid of R. Get rid of M by dividing both sides by M. and get rid of r by multiplying both sides by r. Okay, get rid of the square by taking the square root. And here's the final expression up to this point. Okay, if you were to stop here, because this is probably the first time you're taking physics, possibly after high school. If you've never taken it, obviously this is the first time you're taking physics ever in your life. All right, if you're approaching it from a mathematical perspective, if you're doing it blindly, you may have a tendency to stop at this point. Okay, notice that how fast you're going to spin this is going to be inversely proportional to the mass of the person on the inside. So which means that the heavier the person is, bigger the m is, all right, the slower you have to spin it. Not faster, but slower, if that's the case. Okay, so what's the logic for it? The logic for it is because bigger the mass is, the bigger the tendency for it to go in a straight line, right? So people with larger masses will have a larger tendency to stick to the wall at lower speeds. That's what it means. Okay, and then you're thinking, okay, so you kind of thought that you had to go faster because the person is heavier, right? So that the person would also enjoy the experience. And all of a sudden physics says, which kind of makes sense when you think about it, larger mass means the larger tendency to move in a straight line. So this person is going to be pressed up against the wall harder. All right, so that's the initial assessment if you stop at this point. But then again, if you look at the rest of the terms, obviously this is the radius and you got a normal force. And normal force is not given, but that's not the point. In a conceptual perspective, even from a conceptual point of view, if you guys are looking at what causes N, what causes N? N is a reaction force, guys. What causes N is any force, any push against the wall. All right. So the bigger the mass is, the bigger the tendency for this mass to move in a straight line, the bigger the N is going to be, the normal force is going to be, the reaction force is going to be, because the wall does not want the person to go through the wall. So it's going to apply a tremendous amount of reaction force on it. So which means that N is going to be sensitive to the mass. Okay. So what that means is we have to actually continue with our calculation. So the bigger the mass is, the bigger the N is going to be in essence. That's what we expect. So speaking of N, where do we get N from? Obviously, N is directed towards the center of the circle. And also, N is going to factor into the static frictional force, right? When you actually write out the static frictional force. So N is what we're looking for. All right, so here's my force diagram one more time. All right, so N is the centripetal force in this direction. And also factors into the static frictional force, if you take a look at it. Okay, so harder these surfaces are pressed up against each other, harder they're pressed up against each other, the stronger the frictional force is going to become. And also notice that the frictional force is a force on the y direction. All right, so this is the y direction. All right, so what you need to do is just sum up the forces on the y direction, and it's up. This static frictional force is up. Weight is going to be in the downward direction. This person is suspended on the wall along the y direction. All right, so which means that there's no acceleration on the y direction. So what that means is the static frictional force is going to be the same as the weight. All right, so here's the expression for the static frictional force. Here's the expression for weight. So solve for N, so which means that both sides are going to be divided by mu sub s. And then take this and then plug it into that formula. Okay. And then take a look after substitution. You got a mass here, you got a mass there. Masses will cancel. Boom. So mass is not going to matter. So the minimum required speed for everyone to become suspended, only for a given radius, only is going to depend on the outfit, coefficient of friction of the outfit that the people are wearing. All right. The computations are usually made for smallest coefficient of friction that someone could weigh, and then which means that once you figure that out, once you figure out the minimum required speed, the only thing you have to do is exceed it. All right, so we look for an outfit that's going to generate the least amount of traction, and that's going to give you the minimum required speed. And then the only thing you have to do is just exceed that speed. That's it. All right, somebody's hold on. All right, it's static friction force. So the static frictional force is going to be in the positive y-axis. Absolutely. Just hold that thought just for a second. Okay, I'll give you 5 points for that one. I think that's a good question. Why is it in the positive y direction? I think we need to address that. All right, before we address that, let me just finish this up. All right, so conversions to the metric unit. So plug the numbers in. G is probably about 10. R is in terms of meters, you get this. And mu sub s is going to be that number. And then it gives you a number in terms of meters per second. That's like 12 meters per second. That's 26 miles per hour. Okay, so crucial things from this one that I need to emphasize. One thing is mathematical, and Victor asked the good question. Why is it the static frictional force points in the upward direction? The reason why it points in the upward direction, because gravity is acting on it, right? Gravity pulls you in the downward direction. Friction is opposing the gravitational force in this case. All right. If frictional force did not point in the upward direction, obviously you would be sliding in the downward direction. So that's no good. All right. So the frictional force is opposing your motion. Friction always opposes motion. All right. So that's the whole idea. So gravity wants to pull you in the downward direction, and this static frictional force does not want you to slide. So that's the reason why it's pointing in the upward direction. Okay. There's also a conceptual element to this problem that is important. The conceptual element is, why is it that the mass does not matter? All right. So you thought that the mass of the person was going to matter. You thought that the weight of the person is going to matter. It just so happens it does not matter. when I ask you a question like that, the thing that I don't want to see is don't say the mass gets canceled out of the equation. It does, but it's not a conceptual explanation. That's more of a mathematical fact. All right, it just comes out of algebra. You just follow the rules of algebra. Nature appears to be mathematical, especially in physics, so it works out. That's not what I'm asking. All right, my question is, why is it that the mass of the person does not matter? The explanation comes from here. This formula actually gives you a nice little summary statement. The reason why the mass doesn't matter is the larger the mass is, the harder you will be pushed up against the surface, right? A person who's 2 times more massive is going to experience, a centripetal force, which is going to be 2 times larger. A person who's 10 times heavier is going to experience the centripetal force, normal force, which is going to be 10 times larger. That's the reason why. So it's not going to matter. So the mass is not going to matter as a result. All right, so this question. What is the minimum required speed? Minimum required speed. Okay, what is the maximum speed at which the vehicle is usually going to skid on a curve like this? All right, that change from vehicle to vehicle, that's what I'm interested in. Does it change from vehicle to vehicle? The question is the maximum required speed for a vehicle to negotiate a curve without going into a skid. Does that depend on the mass of the vehicle? If you say yes, then the question is, which vehicles are going to be able to accelerate a curve like this at a larger speed, the lighter ones or heavier ones? Is it a Ford Tempo? Is it an SUV? All right, we're not talking about rollovers. We're talking about literally negotiating a curve without going into a skid. All right, now, if I were to ask you this question, you guys are getting smarter right now. You know whatever it is that you're thinking is not the right answer. All right, because most of you guys, I think, oh, the lighter cars will be able to negotiate faster. I'm telling you, because of how many times I say this, those of you guys who are not listening, that's what you will put on the test. You will say the lighter car is going to be able to negotiate it faster. Ford Tempo is going to be able to negotiate faster because it's lighter. It's got less inertia. All right, so which means that you can bring it up to a larger speed and then just make it turn. Just as easily, you can make the argument that SUV is going to be able to negotiate faster because it's going to experience a larger amount of static frictional force. All right, so the amount of frictional force required for these cars to be able to negotiate this curve is going to depend on the frictional force, and you know the frictional force depends on the mass, right? SUV twice as heavier than a Ford Tempo is going to experience the frictional force is going to be twice as large. So does this mean that the weight of the vehicle is not going to matter? All right. So remember, for you to be able to negotiate a curve, it has to be a centripetal force, and that centripetal force is the static frictional force in essence. All right. So what is the maximum? What is the maximum speed for a vehicle? Negotiate a curve without going into a skid. So the question is, heavier vehicles, do they need to go faster, slower, or about the same speed so that they don't skid? All right. Once again, guys, here's the vehicle moving at a given speed. And at maximum speed, if you're negotiating a curve, the static frictional force is going to maximize. So the static frictional force is maximized at the maximum speed that the vehicle is negotiating a curve. So what happens when you maximize the static frictional force? What happens is the vehicle is going to go into a skid. That's what happens. All right, so you maximize the static frictional force, it's going to go into a skid. So the question is, what is the maximum static frictional force? All right, so the centripetal force is caused by the static frictional force. All right, so generic expression for this centripetal force. And you got the expression for the static frictional force. R is going to represent the radius of the curvature in this case. All right, solve for V. So what you need to do is just get rid of M, multiply both sides by R, and then do your cancellations. And then this is the expression that you get. Okay, once again, if you're not careful, you will stop at this point. It's going to look like more massive the vehicle is, larger the mass is, slower the maximum speed is going to be. Which means that the SUV is going to go into a skid at a lower speed, and then the car, which is because it's less massive, is going to go into a skid at a larger speed. Okay, it almost agrees with your common sense. And it's going to agree with 80–90% of you guys if you're just using common sense. But you have to remember that there's N here one more time. N is a reaction force. It's going to be a reaction force to what mass does. Remember, guys, mass is the measured inertia. All right. In this case, the N is going to come from the weight of this mass. All right. N is going to be a surface force. It's going to be a reaction force to what the mass does in essence. And what mass does is going to experience gravity in essence. All right. So gravity acting on the mass is going to give this mass its weight. And obviously, there's a surface that this car is sitting on. And so there's going to be a reaction force from the surface. So N is sensitive to M in this case. N is always sensitive to M. Because masses have a tendency to retain their initial motions, and then they also experience gravity. All right, so they do have weight. All right, so once again, sum up the forces on the y direction. N is up, W is down. And the acceleration on the y direction is going to be 0 unless this car is just going up and down, bouncing up and down, which it's not. So N comes from W. W is the same as mg, so this becomes your apparent weight. So just do a substitution, back substitution. immediately you notice that the mass is not going to matter. All right, so the mass of the vehicle does not matter. So the maximum speed at which these vehicles go into a skid only depends on the quality of the tires for a given radius. Only depends on the quality of the tires for a given radius. All right, so larger the radius is, the higher the speed at which you can negotiate a curve. The lower the radius is, just like this, the lower the speed at which you negotiate a curve. So there are a bunch of problems with that one. That video, we'll go back and investigate it. That's going to be a nice little discussion. The only thing I need you to know is that, all right, I don't know about Texas. I haven't been there as yet. I can talk about Chicago. On ramps and off ramps here in Chicago is 45 miles per hour. All right, so I'll put 45 miles per hour. Does this mean that you exceed 45 miles per hour and you will go into a skid? No, obviously not. That's not how it is done. Okay, so these are the computations, and they come up with a number for the maximum speed you can negotiate a curve, a ramp like that. It's going to be about 65 to 70 miles per hour. And then on the side of the road, we'll give you a warning speed limit that's like 45 miles per hour. What would that? Would you get a ticket if you exceed it? Not really. No one cares. These are usual warning speed limits, suggested speed limits. The maximum speed limit is about 65 to 70 miles per hour normally. So here's what happens. You're going in this direction. So the reason why you're able to make the turn is because of static frictional force in this direction. And then you go faster, static frictional force is going to become larger. You go fast, even faster, static frictional force is going to become even larger. At maximum speed, this ramp set to, in this case, is 65 miles per hour. So now you maximize the static frictional force. How do you know when you maximize the static frictional force? The tires will tell you they are going to start to screech. What that means is you got 4 tires, 1, 2, or 3 of them are going kinetic, which means the tires start to skid. 3 tires are skidding, 1 tire is not skidding, or then skidding is going to change from tire to tire. At that point, you have to kind of go easy on the accelerator, guys. Accelerator pedal. Okay, just slow down. That's what it means. Because if you keep that up, you're already maximizing static frictional force. That means that the car is going to go in a straight line at a constant speed. You will lose the car. You will lose control of the car. All right, so it says 45 miles per hour. You can literally throttle it up to 65 miles per hour while maximizing your static frictional force, and that's what it is. So why is it that there's such a big discrepancy between the maximum speed and the posted speed? Because the friction depends on the road conditions, right? If it's dry, it's fine. 65 is probably as far as you will go. And if it's raining, this number is going to drop to about between 55 to 60 miles per hour somewhere. And obviously, you guys live in Houston, so there's no snow there. In Chicago, it's snow, so the thing is going to go down further. If it's icy, it's going to go down further. All right, so this is for the max. This is for the worst weather conditions. Usually, just set it up accordingly. On top of that, do something else. This is good engineering.
Building and
maximum speed is set to 65 miles per hour.
modified ZR1 Corvette
Initially, and they still know that people still go faster than that.
is capable of spectacular speeds.
They also bank the road in the direction of the curve. All right, so they will bank it. So now you can negotiate around 70 miles per hour, more than likely. All right, this is banked at 200 miles per hour. All right, they're not going to bank it this way. They don't want you to be right.
Above 200 miles per hour.
All right, so off ramps, on ramps are usually also banked. So you should be able to go up to 70, give and take, if it's a 45 mile per hour. All right, now let's study this. Now that we know a little bit of physics, let's have fun with it. This one, who do you blame for this design? Is that fault? Drivers? Or is it just the city? I got news for you. If I were to get into an accident just like that, driver is always at fault. There's no question about it. All right, you will get a ticket or whatever, that's the case, and then you'll have to pay for it. And more than likely, you're going to end up losing your car on the way. But I would definitely try to recoup some of my expenses. Okay, this is a horrible road design. Right? There's a lot wrong with this road design. And the town, which is responsible for this investment, is also, I don't want to say they're equally at fault, but they contribute to these accidents. This is a horrible road design. Number one, it's too sharp of a turn. It cannot help. I get that. All right. So more than likely, the posted speed limit is way too close to the actual speed limit. All right. I'm guessing that this posted speed limit is probably about 25 miles per hour here. This guy is probably going at 30, and this guy is probably going at 50. Evidently, the maximum speed at which you can negotiate is less than 50 because this guy doesn't have a chance at this point. All right. I mean, the posted speed limit is 25 miles per hour, and this guy is going at 50. Maybe it's his fault. This guy is, once again, probably going over 50. This guy doesn't have a chance. I wouldn't even argue on his behalf. The guy doesn't have a chance. All right, so give it this way, 25 miles per hour. This guy is probably going around 40, and that's fine. And then you're thinking, you're right behind this guy, and you're really irritated with this guy. Obviously, that's when these things happen. Because, you know, if speed limit was probably about 45 miles per hour just before that, and then the speed limit drops to 25, you don't even notice it because that's too much of a drop. And then you're already irritated with this guy, you want to get in front of him, and you think this is a good time to get in front of him. So you get up to 50, and then boom, and you're done. You're done. Okay. And so, which means that the speed limit must have dropped too fast, too much of a drop from the expected speed limit. So people have a hard time adjusting to that sort of stuff. And this is really sharpening up. So now that they designed the road, they should have done a number of things. If the speed limit is going to drop that far, you have to make sure that the speed limit is not very close to the actual speed limit. Okay, in this case, I made that adjustment. You know, probably 45 miles per hour, but the actual maximum speed limit is, they must have dropped it to 25 miles per hour. Most people cannot make that adjustment if the previous speed limit was, say, about 45 miles per hour. You're not going to be able to make that adjustment. All right, so number of things that they should have done. Number one, put a stop sign in front of it, so it slows down the traffic, or speed bump. Should have been a speed bump that would have slowed down the traffic. Merge everything into a single lane. All right, that's going to force people to slow down. And what else? They could have used materials with much higher coefficients of frictions. Right? There are a number of things that they could have done. And this is not banked. Okay, you cannot bank this. It's an underpass. That sort of stuff is really expensive. So you got the lights on, so that's fine. So spend some money on lights. So that's the only measure that. But more importantly, they put a camera up. That's the second investment. That's one of the cheapest investments that you could make. The reason why they put the camera up, in case people get into accidents, they don't want to get sued, or they must have been sued before. So the whole idea, because you don't want to deal with a person like me, a physicist, is showing up there and saying, "Hey, it's a bad road design, so I want some of my money back." So instead, what they did, they set up the cameras. In case of a person who comes forward and say, "Hey, that you guys contributed to this accident," they're just going to set up the camera and say, "Hey, look, this is way too fast." Okay, so a picture is worth 1,000 words. A video is going to be worth 1,000,000,000 words at this point. You cannot argue in front of a judge. No one is going to listen to you. I don't care if even if you have 100 PhDs in physics, they're just not going to listen. All right, so this is the cheapest solution that we came up with. All right, you got the best answer. All right, so the maximum speed with which a car can negotiate a curve, does that depend on the mass of the vehicle? The answer to that question is no, right? It's not going to depend on it. So C is the best answer. So those of you guys who pick C, give yourselves 5 points for that one. That's actually good. Absolutely, yeah. The force of static friction needs to be large enough, right? So give yourselves 5 points. You got it. That's awesome. Okay. Now the non-uniform circular motion. Yeah, we got 5 minutes, my man. Which means that your speed is changing, right? It could be a motorcycle. You're just making the loop, or it could be a car. Remember the car? It was just doing the loop. It was looping the loop. So it starts off at the speed going up against gravity. It's going to slow down, and then it's going to slow down further, and then it's going to speed up. So that's non-uniform circular motion. You usually have multiple forces involved. In this case, so normal force is pointing towards the center. W is pointing away from the center. On top, the weight and the normal force are in the same direction. Here, the weight is in direction. Normal force is directed towards the center. Okay. So how do we figure out the net centripetal force? Okay, here are the rules, guys. If the force is pointing away from the center, it's going to be negative. If it's pointing towards the center, it's going to be positive. F2 is going to be pointing towards the center, so that one is going to be positive. F1 is pointing away from the center, so that's going to be negative. All right, here, N is pointing towards the center, so that's positive. W is pointing away from the center, so that's going to be negative. N is positive, W is negative. So that's your net centripetal force. All right, so here, let's focus on this one. W is pointing towards the center, so that's going to be positive. N is pointing towards the center, so that's going to be positive. All right, here, N is pointing towards the center. W is not pointing towards the center, away from the center, so W is not going to count. All right, so motorcycle, loop in the loop. F, positive or negative, is going to be positive, pointing towards the center. G, positive or negative, negative because pointing away from the center. F, positive or negative, positive because pointing towards the center. Mg, positive or negative, it's going to be positive because pointing towards the center. F, positive or negative, positive pointing towards the center. Mg, positive or negative, neither. It's not pointing away or towards the center, so ignore that one. All right, so that's how we will set up our forces.
Again, according to plans.
All right, so
I'm on the outside helmet cam. Kenny, myself, Loy, Sarge. She does the front flip. Here we come.
So the question is the cable, right? The body cable, which is 200 feet in length.
Going into full velocity right here. Probably
And somehow they knew
reach about 78 miles an hour. Right about here. 78 miles an hour.
78 miles per hour. I'll take that to be about 80. So if we're going at 80 miles per hour, what is the amount of tension that would be inducing on the cable?
You'll see the harness disconnect.
So the question is, did the cable snap? Did they get the wrong cable? Did they get a cable with the wrong tolerance? That's what it is. All right, so this is problem number 6. Compared to the other problems, this is going to be easy. Okay. easier problems that we're doing in class are usually problems that you need to focus on when you're doing the upgrades. Okay, so this is an easier quality problem. Okay, so you do the test, and for whatever the reason, if it doesn't work out, focus on the easier problems that we've done in class because your upgrades will be similar to that. All right, so pendulum move, and so at the bottom of the arc, they got their weight. So there's going to be tension induced on the cable. T is going to be the tension. So tension is going to get larger. The faster you go, the larger the tension is going to be. So it's just common sense. All right, so R is going to be the length of the cable, and these guys are going at 80 miles per hour. The length of the cable that we picked is 200 feet. All right. We got 5 people. I'm assuming that the approximate weight is probably going to be 900 pounds or less. I'm going to give them 900 pounds. And because each and every single person is going to be less than 200 pounds, if you're a daredevil, obviously, these guys tend to be fairly fit. And so what do we have? Miles per hour to meters per second, 50 meters, pounds to newtons, and then kilograms. Okay. All right, here's the setup. Okay, so the bottom has a cable that can handle up to 400 pounds. Okay, here's the setup. This is going to be circular motion. I did the conversions. All right, so if you know the weight, move the decimal to the left. That's going to give you a mass. All right, centripetal force is T towards the center, W is away from the center. All right, and solve for T, so which means that add W to both sides. And that gives you a commonsensical expression. So according to this expression, tension, if you're not moving, depends on the weight. As soon as you start to move, tension is going to go up. That's what it means. The faster you move, the larger the tension is. Slower you move, the slower the tension is. If it's not moving, the tension is the same as your weight. And then you plug the numbers in, boom, 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 go back and forth. And then we'll get expression for the tension that will induce on the wire, on the cable, at 80 miles per hour. So it's going to be a little bit less than 3,000 pounds. And the robotic cable, they can handle up to 4,000 pounds. All right, so which means that the cable didn't snap, guys. So the robotic cable, they can handle more than 1,000 pounds more than what we're going to induce on the cable. So it wasn't the cable that snapped. What happened was, and we have seen this before.
Ready to go.
We're ready, let's go.
An only rehearsal jump. Ready to go.
We're ready, let's go.
Steve and the others don't know is that where this
It's not the cable.
main cable and the
It's the connector.
shorter cables are tight
All right, this connector is not going to be able to handle up to 2,800
taken
pounds.
together.
The mistake is they used a physicist to do the calculations. They should have also had an engineer look at the numbers. Okay, this comes from the strength of the materials. The mechanical engineer or a civil engineer would have known this immediately. And these people kind of overlook that. And that's the reason why it had the accident. So it just simply snapped. It couldn't handle it. Cable was the right cable, but the rest wasn't. We will take a look at. All right, so put down your answers in the chat. Okay, so during a pendulum move, tension on the cable is going to be more than the weight, right? So C is the best answer. So those of you guys who got C on the mark got C so far. Yours has 5 points. So the tension depends on your weight plus anything related to your speed. So faster you go, the larger the tension is going to be. Okay, this time you guys got it, right? It's going to be easier to hold a partner when he's not moving because as soon as he starts to move, the tension is going to go up. All right, yours has 5 points for that one.
A brutal and punishing run.
One of the boarders is Ryan's boss, Brian Schaefer. Ryan owns the skate park and is the tournament's organizer. Brian decides to get in on the action and try his luck at the loop.
He gave it a few attempts, and at first he didn't make it very far, but he made a couple that I think if the pads weren't there, then he would have made it.
But as Ryan continues to practice, his runs become more disastrous. The padding is pulled away, and several riders nail the loop. Now the pressure is on for Brian.
I was anxious because I wanted to do it. I was nervous because I knew how dangerous it was.
Brian takes off and falls short.
The whole crowd was like, yeah, put their hands together. Come on, Brian, go do it again. Give it another try, that type of thing. He was thinking, hey, it's now or never. I was thinking the same thing.
Brian steps up and goes for a ride that no one will ever forget.
The impact was just tremendous. You could hear it from where I was standing. I was probably about 30 feet away. As soon as he fell, it was dead silence. And then the first thing I heard was, paramedic! I grabbed the microphone and just cleared the crowd. I just saw like, well, maybe he'll be okay. He'll get up in a second. until I walked up there and realized he was out. His neck was kind of crooked, and he was just laying there totally limp.
Ryan's dad, Bill, is in the audience.
They worked on him on a ramp for a while. He was totally unconscious and looked bad. When I saw him hit the deck, I felt that he hurt himself pretty bad, just by the angle and the way he was down. I was feeling more afraid that he would be paralyzed.
Brian's in bad shape. Medics know they must be careful with his neck. One wrong move could cost Brian his life. After they stabilize him, medics carefully wheel Brian to an ambulance and then rush to a Tampa trauma center. Incredibly, Brian suffers only a concussion and a broken hand. It was fate that spared his spinal cord from massive injuries. Although the accident threw Brian's memory for a loop, he can still recall his fateful ride.
Going into it, I just remember feeling like this is the one. I come down the ramp and realizing I was a little too far to the right, which basically threw me a little off course. But I had no idea that, it would have been as dramatic or as bad of a fall as it was. But I was pretty shocked to see how fortunate I was to come out of it and not possibly being paralyzed. I think I have something to refer back to now to realize how fortunate I am and to take advantage of life as much as possible and don't take life for granted.
So here's a question for you. Here is a question.
But as Brian continues to practice, his runs become more disastrous. The padding is pulled away, and several riders nail the loop.
Why is that he's not able to complete the loop? Why is he not able to loop the loop properly? I mean, obviously, it's doable.
Brian continues to practice. His runs become more disastrous.
All right, so he's not able to do it.
Away, and several riders.
But these guys are just fine.
Nail the loop.
So why is it that he's not able to do it and the other guys are able to do it just fine? Any ideas? Any suggestions?
He's not reaching the velocity?
Okay, you could say that he's probably not reaching the minimum speed required to complete the loop, right? Okay, you can certainly make that argument. So my question is, are they all starting from the same point? They're all starting from the same point. Or you engineer something like that, believe it or not, guys, the starting point usually should give you the minimum required speed to complete the loop.
Continues to practice. His runs become more disastrous.
All right, so which means that this guy must be doing something that he's not supposed to be doing. Which is what? Okay, so
exerting enough pressure on the ramp itself to stay on it.
Okay, so Mark, I'm going to give you 5 points. And every single person who commented, he's not generating enough pressure on the ramp.
Brian continues to practice.
Okay, not a bad answer either. Okay, the best thing to do normally is figure out the minimum required speed and then exceed it. Okay, so if I'm doing a ramp design like that, I would just put your starting point in such a way that you would have the minimum required speed. You would have a little bit more than the minimum required speed normally by design. Okay, so how do I do that? All right, so what is the minimum required speed? How do you figure that out? So I'm going to put emphasis on that one. Because the only thing you have to do is figure out the minimum required speed and then exceed it. So what is that minimum required speed right at that point? Okay, so how do you find out what the minimum required speed is? All right, number one, at that point, you're going to be upside down. So obviously gravity is going to be acting on you. And then notice that you're also pressed up against the wall, the ceiling. So there's going to be a normal force acting on it, right? Normally, if you have a large enough speed, if you're pressed up against the wall, so you got gravity, you got the normal force at that point. All right. So what we'll do is just, we're looking for the minimum required speed. Radius is given at this point. All right, so gravity is the only force acting. I'm going to redraw this because I want to get my forces in. This is the radial direction. The radial direction is, I should have put R in the dominant direction. It should always point towards the center. That's fine. It's being careless. So you got your W, you got the normal force pointing towards the center. All right. So because I'm looking for speed, I have a generic expression for centripetal force. That's the centripetal force is the net force on the radial direction. It's pointing towards the center, W is pointing towards the center. So which means that the net centripetal force is going to cause this mass to accelerate in this direction. All right. Now, for me to be able to figure out the minimum required speed, there's a trick involved. It's comes right out of physics. We'll find the trick explanation right here. It says minimum required speed will experience apparent weightlessness, which means that you will feel weightless when you're upside down at the minimum required speed. All right, if you never experience that, that's going to be terrifying at that point. Okay, you really have to overcome that fear, because literally at minimum required speed, your trajectory of your motion. All right, at minimum required speed, the trajectory of your motion is going to match the curvature of the inside of the wall. Okay, so which means that you will feel weightless at that point. Okay, I mean, that requires a lot of courage and it requires a lot of practice. At the minimum required speed, you're upside down, you're feeling weightless. So which means that n is going to be 0. That, but in the minimum required speed, n is 0, so speed is the minimum required speed. You know your W is mg, and then masses will cancel. So the minimum required speed is only going to depend on the radius of the curvature of the ramp. All right, so in this case, it's going to be, then if I know what the minimum required speed is, I would just, there's a way to calculate this. So this is something that we'll do next week. I would figure out the height required for your initial starting point. So it would automatically give you the initial, it would give you the minimum required speed. What you need to do is you need to exceed the minimum required speed. So number one, you should be aware of the fact that you're going to feel almost weightless. And then the other people just crouch down real fast, and you have to commit to it because you will be upside down feeling weightless. That sort of stuff requires a lot of commitment. So minimum required speed, hold on, minimum required speed is about 12 miles per hour, right? So what you need to do is, this is the magic number. If you're under it, if you're upside down, that's not going to work. You can hurt yourself. And you have to be over it. So you have to be like 13, 14 miles per hour. You will, it's still, sort of stuff requires a lot of courage. This is not something that most of us could do. Obviously, you have to be a bit of a daredevil for you to be able to pull something off. Ryan evidently does not have what it takes because he's just, every time he does it, he gets more and more scared. This is a confidence game. If you're not confident enough, you cannot execute something like that. And then that's the reason why he started to go towards the edge, because when he started to give up on it, you know, he thought that there was something that he could grab, and of course there was nothing there. So ended up hurting himself pretty badly. Yeah, you wanted to say something. Somebody wanted to say something.
I was just wondering why the normal force went to 0. I was just confused.
Okay, that's you give yourself 5 points. The reason why the normal force goes to 0 at minimum required speed for you to be able to complete the loop, what happens is the trajectory of your motion at that point matches the curvature of the inside of the wall. Okay, because it's projectile motion at that point. All right, the minimum required speed, the trajectory of your motion when you're upside down, and that's what the problem says. It gives you a hint. So that at the minimum required speed, you will feel weightless. So the condition of apparent weightlessness is created for a brief moment at that point, because the trajectory of your motion is going to match the curvature of the inside of the wall at that point. So which means that n becomes 0, which means that literally, despite the fact that you got the skateboard under your feet, skateboard is touching the ceiling of this wall, but it's not generating any pressure on it. That's what it means. So n becomes 0 at that point. So that's going to give you the minimum required speed. The only thing you have to do is just exceed that speed. All right, real life case looks like that. Instead of just talking about it, watch this. This is beautifully done.
Good demo? Yeah, good.
My name's Dan Walters, and I'm a stuntman who does tumbling, gymnastics, and parkour. I'm attempting to run the loop. So I've seen people do it on a skateboard before, I've seen people do it on a BMX before, but no one's ever tried it on their feet, so it's been nice to be the first guy to actually run it. It looks a lot bigger than what I thought it was going to be. Yeah, it must have been not the easiest thing I've ever done. To be one of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further and see how far people can go.
Basically boils down to this centripetal force. You need to keep on accelerating. So you need to reach a certain speed. And I've worked it out. It's quite good news, actually. The speed at the top is 8.65 miles per hour. That's it.
Okay, 3, 2, 1, go. 17.
Can somebody show me that one back? Well, this one's it. I know I've said that 3 times now, but this one is it. Well, I'm close, I reckon I'm close. Getting close. You can't really go any further until you take the match out. Yeah, go for it.
It's really well done. Okay, so everything that we discussed, number one, Required speed was almost 9 miles per hour. All right, so that's the minimum required speed in order to complete the loop.
Basically,
and then
it boils down to this centripetal.
17.
So this guy's capable of 17 miles per hour. But guys, in a flat surface, 17 miles per hour is okay. But can you actually get up to more, say about 10 miles per hour in a loop like that? He knew he could do it. At the same time, he noticed that it's a confidence thing. All right, so he started building up his confidence. And eventually, he noticed that, hey, once he was confident,
you can't really go any further.
So the only thing I don't like about it, it's done by Pepsi. Should have been Coke.